Assalamu alaikum. This is Dr. Usman Sadiq Paracha, and today we would be having our lecture number 24 of the subject Applied Quantitative Analysis and Practices. Previously, we would had a discussion about the regression and its main concept, and continuing that, basically we went on to discuss the measures of variation, which basically form the foundation of the regression concept. And here we had the graphical representation of the same concept there, and how we used to measure the explained variation and unexplained variation, which was denoted by SSE and SSR, whereas SSR is the sum of squares for regression, which is the explained variation, and then we had a sum of squares for errors, which was unexplained variation. Combination of both these two form the total sum of squares, and when depicted graphically, it gives us the concept of how these two terms make the foundation, and thus help us in determining another important concept which we discussed before, and that's called coefficient of determination. Now here, coefficient of determination, R square, we discussed before, was related to the division of SSR with SSE and or SST, sorry, and in this case it gives us the variance which is explained by the independent variables for the dependent variable here. So that's why R square here is of quite a major importance here, and R square calculation is totally based on measures of variation here. So that makes our concept of measures of variation very important from that aspect. Then we had an example of coefficient of determination, and we just came to know how to go through the calculation in this case, and how R square is depicted in the form of different diagrams, and how different values, when they are scatter plotted, what kind of pattern would depict what kind of value of R square. So basically, again, as we know that correlation coefficient is determined by R, and the square of it, R square, is basically coefficient of determination. So once we do scatter plot relationship between two variables, then it easily gives us the R square as well. However, then going through different examples and the patterns which were available, we just went into the concept of standard error of estimate here, and here we discussed how basically the error is there and how it's calculated, and again, the bigger the value, and the value benchmark would be the scale of the dependent variable. So if it's below that scale, then standard error of estimate is considered to be very small, and that's why its inclusion is very necessary, because R square and standard error estimate are kind of related. So if standard error estimate is larger, then definitely we have got a weaker coefficient of determination, because the error terms are there quite large. So both are interrelated and play an important role in the interpretation of the model. And then we have the various assumptions and the conditions which are required for regression. Again, there were some conditions which had to be applied before the regression test was conducted, and in this case that was applicable for the variables which were inculcated in the regression at first. So the data set initially would have to be checked for the separate conditions which are kind of same, which are enlisted here. And the reason is that we have to check it both times, reason being so that the final regression variate, as we say it, basically we have to check its assumptions and see whether the conditions it's meeting is true or not, and what's the nature of the residuals there after regression analysis is performed. So that's why it's important that the error term or residuals basically, or residual analysis, fulfills these additional conditions as well, in addition to the the assumptions which we have already made for the data set which was initially being considered for the regression test. So we discussed these one by one, and we would be discussing them in detail for SPSS as well. So the concept here based upon the linearity, we discussed how linearity is important, and then there should be independence of errors. Likewise, the residuals should be normal, and there are conventional tools to check the normality. We have discussed it before. Likewise, then there is equal variance which needs to be ensured so that we can ensure homoscedasticity. And then we had a discussion about the slope, how we can infer about the slope basically. So we went through all these details, and just to have a recap, this was the model, initial model which we discussed regarding regression. As you can see, the standard equation and the intercept and the slope coefficient which we discussed before. Then likewise the inclusion of independent variable and the random error term which needs to be inculcated there. So this is the same form we have discussed before as y is equal to mx plus c, which you might have studied in your earlier grades. So this was the prototype model, and graphically we depicted this model in this form, and we discussed about it how an error term for each individual value can be calculated, and we have magnified these small values so that we can have a detailed outlook on how this whole phenomena works. Then we had a discussion that which methodology is to be followed for linear regression model, and we discussed that the normally least square method is formed, and in which it does make sense to take sum of squares of these values, because as you can see here that the positive values would nullify the negative values if we what we have to do is just take the sum of them. So taking the sum of them only is not the solution. So we have to take the sum of squares basically of the terms around the means of the y. So basically that was the concept which was encircling this whole graphical presentation. Then we had discussed about the layers of variation, and again we discussed that what do we mean by SSR and what do we mean by SSE here, and how we can calculate total sum of squares. And graphically we displayed this in this form, and from here we can easily see that what's the explained part of this single point observation, and what is the unexplained part, also termed as SSE or sum of squares for errors. So basically based on that we calculated the coefficient of determination, R square, which we discussed that in detail. As you can see here, the formula is SSR divided by SST. So again, like correlation coefficient, R square ranges in between 0 and 1. And then again 0.5 and above is considered a strong value, but it's not necessary that 0.5 or above values are obtained. But sometimes, or even most of the times, R square value of even 0.1 or 0.2 can be termed as a significant contribution towards literature, because previously maybe the relationship being studied in between the similar variables among other industries may have reported R square even less than 0.1. So in your new study, if R square is reported to be greater than 0.1 or 0.2, then it would be quite an contribution towards the literature, as previously the evidences proved that the R-square value proved to be less than this value. So this is not a rule of thumb that R-square value should always be 0.5 or greater than 0.5. R-square value can come down and it can be even low, but it depends upon the theoretical perspective and the theoretical model which you want to study and which you are studying basically in your work. So based on that, there are different interpretations for R-square, and as we have discussed before, its importance is quite evident. So R-square here basically explains quite a bit of the picture between the two variables, and technically speaking, this is how the results are displayed. But then again, the display of the results vary from software to software. So here basically you can see we have already discussed this before, how regression is displayed here and how R-square is calculated. Then basically in this typical example, we did come to the conclusion that 58% of the variation in house prices was explained by variation in the size. So then we came across the standard error of estimate here, and we discussed the formula here, how basically this is presented and what do we mean by standard error of estimate. And then we discussed that how it is displayed in the results, and again we discussed the standard error basically must be compared with the range of the values independent variable, and if when compared with that, this value can be decided whether it's small or large, and then the verdict for regarding that decision can be passed. So basically standard error of estimate is again an important term and is used frequently. Then we discussed that what do we mean by small standard error values, and in that case what would be the graphical presentation. And in that case you can see that if these values are large and these values are more scattered around the main line, then what would be the depiction in this case for standard error of estimate here. So this was just a comparison diagram. Then we discussed about the assumptions and how we have to test them. We would be discussing this in detail in the coming lectures. And these are the same typical assumption, but the difference is that these assumptions need to be met specifically for regression variate and for the error terms called residuals. So they are equally important in this case. Then we did discuss about the residual analysis and how it's important and what do we have to evaluate. Typically we have to evaluate all the same things which we have been evaluating for the initial data set, basically when it was about to be inducted for analysis. Then we discussed about the various patterns, what was the residual analysis and what do we mean by these patterns, which patterns are right, which patterns are wrong, and how we are going to judge them. Likewise, these analyses also give us an idea of independence of errors. So which kind of pattern would be accurate and which won't be accurate. So this was the depiction of those results here which we discussed before. Likewise, how to check for normality for residuals. These are the same conventional methodologies we have discussed before, like stem and leaf, box plot, histograms, normal probability plot, and the only difference is that we are considering residuals here instead of the original data set and original values entered in the data set then. Then how would the residual analysis for normality would look like, and again we are looking at a PP plot, and again we have discussed that these values should be more closer to the baseline here. The farther they are, the more problematic the whole this diagnosis is. So then what would be the pattern for showing equal variance among the data set? And as you can see, we have discussed how and what kind of pattern would portray that there is constant variance and what would be portraying that there is a non-constant variance here. And we had an example of a practical problem and how these values have been put across the same plotting on the same diagram, and it doesn't appear to violate any regression assumptions here. So we moved on basically about the inference about the slope. Now in inferences about the slope, basically we had a brief discussion that basically this is a standard error of that regression slope, which is calculated by a certain formula. And again, this standard error does include the SSE, or in other words, basically the standard error of the estimate. So here you can say that basically the formula does give us a brief idea of the standard error of the regression slope coefficient B1, which is of primary importance to us, because this slope gives us the relative idea of how much unit change in independent variable would cause change in dependent variable. So that's why the standard error of such kind of slope coefficient is of major importance. Then again, the important problem regarding the slope is the t-test. And why do we have to apply the t-test? The reason being so that again we have to test our hypothesis, because though we do have a certain kind of data set and we were able to draw some kind of figure which would be telling us that this much unit change in independent variable would be causing the change in dependent. But the issue is that as we are dealing with social sciences and in business studies, so in business studies again, as we are not able to take the whole population and we are taking the sample, then we have to basically make a probability that how much it is possible that if we take another sample from the same population and the values of this slope which we have just obtained would be greater than 0 in this case. So again, in order to get the probability of that, then we are dealing with sample statistics. So here, in order to test such a statistic, we apply t-test. We have already discussed about z-test and its application and its implication. So here in this case we have to apply t-test. The formulas would be different. So here the question for this kind of inference is that would there be any linear relationship between the two variables. Now again we have got two hypotheses which we have discussed before, and one is the null one, in which it is stated that there is no linear relationship. And on the other hand, we have got the alternative hypothesis, which is denoted by H1 and which speculates that beta 1 would not be equal to 0, or in other words, linear relationship would exist. However, mind you that in this case, we are not saying for sure that the beta would be equivalent to certain value. All what we are able to comment upon is that would there be any kind of relationship or not. So that's the nature of probability we have been discussing before, and that's what is calculated. So in order to calculate these test statistics, we have got a certain formula here which you can see, and in this case it's quite evident that basically it's the smaller beta 1 minus larger beta 1 divided by the standard error. Again, here basically is the regression slope coefficient and the hypothesized slope, and then again we have got the standard error. Then is our degree of freedom, which is n minus 2, and again the degree of freedom concept states that basically how much positions you have available for placement of your values. So in order to have more degree of freedom, definitely we should have more observations per variable. The greater are the number of observations per variable, then again the more space we have for degree of freedom, and that does make a lot of difference when we are trying to speculate about our testing of these null and alternative hypotheses. So basically it's not just about calculating a value through regression and getting a slope value and ultimately forming an equation. It's more about also that, okay, we did get some value, we did get some estimate. The issue is that in that specific population, if we try to extract some other sample, how much it is possible that this relationship will still exist. So in order to answer that question, then we have to go through the exercise of basically giving the same null and alternative hypothesis statements which we have been doing before, and then again in order to test that we have to apply some test statistic, and in this case the t statistic is more commonly followed. Now here basically we have got an example here in which we are given house price in 1,000, and you can see that also we are given the size of the house. Now here we have discussed that this was the estimate which we calculated from the data which was given to us, and again this is the estimated regression equation in this case. Now here you can see that the slope of the model is 0.1098. Now question is that is there a relationship between the square footage of the house and sale price? Now in this case we have to go cautiously because we have to test our hypothesis in this case, whether such a relationship exists and how much probability is there that it would be applicable for the same samples, more samples which have been extracted from the same population. So here we can see the computer generated result, and you can see the coefficient which has been calculated, and here you can also see the standard error which has been calculated here. Now we have been reported a t-stat value here which is set to be 3.32, and again this has got the p-value of 0.01. Now this value again is less than the value of 0.05, so we can move ahead with our conclusion here. So basically we have already discussed the calculation of the same type, but again the difference in previous examples which we had done was that those calculations are more focused upon basically the t-stat, or in fact sorry, the z-stat value and its respective p-value. So here the difference is that now we are more focused upon the t-statistic here. So how this value has been calculated, let's have a look at this phenomena. And again, as you can see that we just followed the same procedure which we did follow for z-test, and here you can see that we drew the same probability plot which is here, and we basically identified the level of significance which was 0.05, and we identified the regions here and the end regions here which you can see here and here, and we can see that 0.025 and 0.025 have been identified on both sides. Again, this does portray to us that basically this is a two-tailed test. So we are not sure about the direction. Then we did identify that in which region we would be rejecting our null hypothesis and in which region we won't be rejecting any null hypothesis. So our value here, which we had calculated before through that formula, t statistic was 3.329. So we have to plot this value on the same probability normality graph, because again, as this data set is normal, so by plotting it here we can clearly see that in the end regions which we have defined, and again you can very much see that for t statistic these critical values are different. In z test you might have remembered that these values were 1.96 and plus 1.96 for z test. Now here we are dealing with t test, so the critical values are different. So we have plotted this t stat value, which is 3.329 here, and as we plotted, it is coming in the rejection region. Now here, as this is coming in rejection region, so we have to reject our null hypothesis. So based on that, we can conclude that there is sufficient evidence that there is a relationship between square footage and house price, and square footage does affect house price. Though we have discussed about this sufficient evidence, which we have discussed before, and in this thing you can clearly see that the criteria was that the value should either fall on rejection region or non-rejection region, and based on that we did come to the conclusion. But again, you can see that the important aspect of any kind of test statistic is its p-value, and we have discussed about that before. So here in our report we are given the p-value, and basically it's the p-value based on which we decide whether the null hypothesis is accepted or rejected. So here you can see that the p-value is less than 0.05, and here you can see the alpha. So as this p-value is less than this alpha, that's why we reject the null hypothesis. And again, we can conclude that yes, based on the sample technique, it's very much evident that there's a positive relationship between these two, and the size of the house does affect the house price here. So this is the same procedure which we have been doing in the past regarding z-test, only the difference was that we were having different formula for z-test, and here the t-test formula is different. Likewise, there's also difference of critical values. So based on that, once the critical values are changed, then again the rejection and non-rejection regions have also changed. So based on that, the acceptance criteria for null hypothesis is also different for t-test here. Then again, the other important part is regarding f-test for significance. Now here f-test basically gives us a general concept of the whole model, because in t-test you might have seen that basically that was related to the inference about the slope of that specific single variable which is being tested. But here an f-test statistic is used to identify whether the whole model basically is valid or not. So in this case we do calculate this f-test statistic, and we have got the formula here in this form, and you can see it's MSR divided by MSE, whereas MSR basically is focused upon sum of squares for regression, whereas MSE basically is focused upon the sum of squares for errors here. So basically the degree of freedom also has its part here, and based on that we do calculate the final F statistic, which then is further used to validify whether the model is valid or not. So these are the results for F test for significance in case of the data set which we have been discussing before. And in this you can see that F statistic is clearly mentioned through the formula which has been there. We calculated the value, and we also calculated how many degrees of freedom we have in this case, which is quite important. Then again for F test we are also reported the significance value here, which is quite evident, and this significance value basically is based on the p-value, and we have to compare it whether it's less than 0.05 or not, which is the standard benchmark for our level of significance. So if this is significant, which you can see, then we can accept that the model is valid. So here we can see how this whole phenomena works. So here F test basically has also to be tested for significance, and again in this case we also have to prove our null and alternative hypothesis, and in this case you can clearly see that normally this F statistic basically is more like the calculation which gives us a certain value here, and you can see it's 11.08 here. We also are given the level of significance here and degree of freedom, which is in this case for 1 is 1 and df2 is 8. So our critical values here, as this is basically one directional hypothesis, so we have taken alpha equal to 0.05, and the F value basically which is critical here is 5.32. Now based on that, if our value falls within this range, then it's not null hypothesis is not rejected, otherwise the null hypothesis has to be rejected. So as our value of F statistic is ahead of this F.05 equal to 5.32, that means that we would have to reject our null hypothesis, and thus we can come to the conclusion that there is quite much evidence that house size is affecting the selling price. So F test basically is used to evaluate the overall model, and again it must be mentioned that all these tests are necessary for a regression performance, for finding out the various results for regression in this case. So we have to also calculate the confidence interval estimate for the slope, and here you can see the standard formula for calculating the confidence interval here, which is represented here through beta 1 plus minus t alpha and divide by 2 into standard, which is the standard error. So basically we are given the lower and upper level of the confidence interval here and the relevant coefficient. So through this formula, this whole confidence interval estimate can be easily calculated. We will discuss in detail about that what is the concept behind confidence interval here in this case. So likewise then, once this is found out, we can also try to see that what are the upper and lower end limits, and here you can see very well that basically we are 95% confident that the average impact on sale price is between two specific values, which are the upper limit and lower limit here, which you can clearly see here in this table. So basically here this 95% confidence interval in which we have taken alpha value as 0.05. So it does not include 0, and thus it is portraying that there is a significant relationship between the price of the house and size, so at a certain level of significance. So once we have gone through that, then let's have a discussion on the confidence interval estimation before we would commence with our regression discussion. Basically, in confidence interval estimation, it's a point estimate and it's a single number. Then confidence interval basically gives us the additional information that how much variable that estimate would be and how it can move around. Its lower confidence limit and its higher upper confidence limit in this case. In order to calculate, basically we do have the same parameters which we have discussed. That is, for population we have the notification of mu here, and then for proportion this is basically pi, and then we have got sample statistic which is represented by x bar and proportion by p. So these are various notations which we give for these point estimates in terms of confidence interval estimation. And once we have gone through that, then our question would be that how much uncertainty is attached with this point estimate of population parameter. Now basically in this case we have to be sure that to what extent this value can fluctuate around the positive side or negative side, and in order to calculate that we have to calculate an interval estimate which would give us more information about that specific population instead of a single point estimate which won't give us much information in this case. So these interval estimates are then also termed as confidence level or confidence intervals. So when we are discussing about these confidence intervals, then we have to basically also talk about the confidence interval estimate here. And basically an interval, it gives us a range of value between which the point estimate can lie around and how much maximum fluctuation is possible. Because again, there would be difference of values and it would be varying from sample to sample. So these observations which we presently have been conducting, they are drawn from only one sample. So basically based on that one sample, coming to the conclusion that this would be the exact value of point estimate would not be right, and that's why we do give a confidence interval estimate which would give us a faint idea of how much fluctuation would be possible for that point estimate both in positive or negative direction. So here basically in this case this whole phenomena gives us the information about the closeness to unknown population parameters, and it is basically stated in terms of level of confidence, which can be 95% confident or 99, depend upon the nature of data and results. So here basically we are taking an example so that the whole concept can get clear. Now this is a serial fill example in which we have got a certain population which is equivalent to 368, and then we have got a sigma value of 15. Now here if we are taking the sample size of n is equal to 25, then the end confidence interval estimates can easily be calculated through the formulas which we have been given. And here when we deploy these values in confidence interval formula, you can clearly see that both the positive end side and positive end limit and negative end limit have been identified. Now here according to our speculation, 95% of our intervals should be formed in this manner. Now once you don't know the mu, because we seldomly know any information about the population, then we know that we have to replace this mu with x bar. And here x bar basically is 362.3. So while going through the calculation, we can easily depict that the interval is 362.3 plus minus 1.96 and the rest of the values. So we have got two end values in this case, and among which the mean of this whole data set would be there, no matter how many samples we may be drawing from the main population. So there would be quite a possibility that this value would be lying on that. So here basically once we have known these limits, so we can state them as mu is greater or less than these specific values, and basically this interval based on this sample gives us a correct statement about the population. So then what about the intervals from other population samples? So here is basically a chart. Now in this chart basically there are 5 different samples which have been taken. Again, they have got different means, and we have got different lower and upper limits for each mean value identified. So we have calculated the confidence interval for each value differently. But again, among all these values, only there was one possibility in which it might not have contained our population parameter. So normally confidence interval do give us a very good idea of how much far or less we can go about regarding our calculation of this basically mean value. So here basically this is vital for confidence interval, and then in practice we can only take one sample size, and again we do not know the population mu. So here also we know but that 95% of the intervals formed through this methodology would contain the mu here. So basically based on that one sample, we have selected that we are 95% confident that our interval would contain mu here in this case. So this is basically a 95% confidence interval in this case. And again, it's a note that 95% confidence is based on the fact that we use z is equal to 1.96, so hence it's true for here in this case also. So our confidence basically is based on that same 95% confidence interval that our main value, which has been calculated from the sample, should be there in population as well. Now based on this, then we can come to the same conclusion, and this is the estimation process, that we have got a certain population, and you can see that from that population basically we have extracted a sample which is kind of small compared to population, but anyhow we did withdrew the sample, and in this case our mean of the sample was found to be this. And again, by applying the confidence interval formula, we can say that we are 95% confident that our population would be in between 40 and 60, depending upon the confidence interval which has been calculated in this case. So here basically the general formula for all confidence interval basically is the point estimate plus minus critical value into standard error. Now here basically the point estimate is the sample statistic which is used for estimating the population parameter of interest. Now critical value basically is the value which is based on sampling distribution, and its value is calculated from that distribution for point estimate and desired confidence level. Now these are the basic grounds for conducting this self-test. So here we have also got a standard error, which is basically the standard deviation of the point estimate. So same concept of standard error exists here for point estimate also, and again we are talking about the same kind of critical values which we have been discussing before. And again the formula basically for confidence interval has already been discussed. So here basically confidence level is regarding the confidence the interval will contain the unknown population parameter. So basically we are dealing with probability here, and then again we are dealing with the percentage, which is less than 100%. So now here we can say that in order to determine the confidence level, we have taken the value of 95%, and 1 minus alpha here then can be given as 0.95, or alpha is equal to 0.05. Now this frequency interpretation basically is regarding that 95% of this whole confidence interval that has been made will contain this unknown true parameter. Now basically it's not possible to claim that kind of heightened expectation that a specific interval will contain or will not contain the population, your true parameter here, because there is no probability involved in this specific interval. So here basically 95% of all the confidence intervals that can be made will contain this unknown true parameter. Again, that's possible that though as there is no probability which can be calculated for that specific interval, then basically we can say that it may contain that true parameter or it may not contain that true parameter. So here basically again confidence level here gives us a faint idea of the probability of whether which kind of value will fall where, and how much probable it is that the same value will be repeated if we are taking the same sample or same kind of samples from the population. So then here again we have got two options in which confidence interval can be calculated. First is the case in which we know the population mean, and then our standard deviation in one case is known and standard deviation on the other hand is unknown. So basically we also have the population promotion, which is presently not in our scope. So coming to the assumptions, basically what are the important assumptions for confidence interval for this population mu, and specifically when we have known the standard deviation. One is that the population standard deviation should be known, that's already classified. Then another important aspect is that the population should be normally distributed, and again if it's not normally distributed, then we have to do the treatment, and one possible thing is that we should use large sample with n greater than 30. In this case again the confidence interval estimate formula is given, which is portrayed by x bar plus minus z alpha by 2 with the sigma divided by under root n. So this is the formula which is used to calculate the confidence interval estimate here in this case. Through this formula we basically calculate the upper end limit and lower end limit, and it is important to know this confidence interval first, because afterwards the whole test liability and the whole test credibility will lie on the correction of these values. So based on that we have drawn the concept that how to find the critical value z here. Now here we are given a 95% confidence interval, and the end values are clear-cut portrayed here with alpha by 2 is equal to 0.025. We basically identified the central region in which the hypothesis would be accepted, and if the value comes here, then we are bound to prove it that the null hypothesis basically is true if the value lies in the middle region. Now here basically we are given the z value for minus 1.96, and then we have got z values for 1.96, which is in the positive direction. So here you can see that we have tried to calculate z alpha by 2, which again would be 1.96 in positive direction and minus 1.96 in negative direction. So it's the same procedure which we have been conducting before, and we have done numerous examples of how to calculate the probability and how to draw this normal probability plot, and then again how to find out the various values with specific level of significance. So based on that, let's have a look what are the common levels of confidence which we use. One commonly level use of confidence level is 90%, 95% and 99%. And now here basically you can see the values which are commonly used, and then again basically how let's say for 80% what would be the confidence coefficient here, and what would be the relevant z value here in this case. So you can see that slowly when we come to 95%, the z value is also increased, and likewise we have calculated the confidence coefficient as well. So likewise we have got relative values for different confidence level like 98%, 99% and 99.8%. So these are different confidence levels which are used depending upon the field in which the study is being carried out. For example, if the study is being carried out in medical sciences, so this confidence level would have been 99.9%, because people would like to avoid basically any kind of risk in calculating any crucial figure having basically less than the confidence level of 99.9%. So this basically is the explanation of the whole confidence of level basically which is commonly used. And here you can see we have got certain sampling distribution, and you can clearly see the acceptance regions and non-acceptance region which are portrayed here, and we have also got the mu value which is depicted here. Now here basically the confidence interval on this whole thing lies in different position, but it does revolve around the mean value. And again here you can see the x1 and x2 dilemma, and also we can see that how the intervals extend from these two values which we have discussed before, and then based on this only one reading was abnormal, which was a bit away from the normal set. So basically here we can say that 100% of intervals constructed do contain population mu and 100% do not. So now here basically we have got certain example, but that would be covered in next lecture. In today's lecture we discussed about the inference about the slope, because inference basically is an important part. It gives us the exact magnitude of the unit change in x or independent variable which can cause change in y or dependent variable. That's why we have to be sure about the inference here, and that's why t-tests are calculated for slope as well, because again at the end of the whole calculation we are basically calculating the slope for a specific sample. So we again have to calculate the probability that how much possibility is there that there would be certain kind of relationship which might exist between the two variables. So in this case, in order to ensure that and in order to see that this goes through, we again formulate the null and alternative hypothesis, and then we apply the test for calculating the probability which is there for the same value which would come as a result if other samples are drawn from the population. So in this case we conducted the t-test, how to calculate it and how to then compare it with level of significance, and then how to pass the verdict whether this hypothesis of null hypothesis is true or not. So we had a detailed discussion about that. Then we took a practical example of t-test, and then how the values which are reported in software can be used for the inference about the slope, and at what level these values can be accepted or rejected. So coming to this whole aspect of t-test, again this kind of calculation we have already done for z-test, but t-test basically is carried out for evaluation of the same probability when we are considering regression variates. So in this case, another important test is the f-test, because then we have to calculate whether the whole regression model fulfills the criteria, and the results, would they be same if other samples are drawn from the same population. So here, that's why we calculate the f-test, we deploy the f-test. It has got its own certain conditions, it has got its own critical values. Likewise, t-test also has its own set of critical values which are different from z. So based on these critical values and the plotting which has been done, we would try to ensure that f-test value would lie within the range which is acceptable. So once this f-test is conducted and is basically considered to be significant, then we can conclude that our whole regression model is portraying the same value and would be giving the same value when the same test is conducted on other samples. Likewise, we discussed about the confidence interval estimate, how to go through that, how to calculate it, and how these values carry interpretation for the test which we just conducted. So what was the concept behind that? That was also discussed, and then we had the calculation drawn, and what was the typical formula used in that aspect, and how we can carry out various calculations for confidence interval, and what would be the interpretation for the whole model in this case. Thank you so much. Allah Hafiz.